This is a very good book that we will use in ET-260 and then ET-341. For now, we will just concentrate on the very important topics. First, we begin with approximations. Imagine that we have a resistor that's 1%. So it could be between 989 ohms and 1010. But without anything attached, we say that it is a 1 kilo ohm resistor. So this is an example of the first approximation. In looking at the circuit above, we can't say what is the output that will be delivered to the load because the internal resistance is 1 ohm and the load is 5 ohms. In this case, we would need to do some calculations to see what is the true output. This is an example then of the second approximation. Simply means more calculations. Imagine that we have a transistor operating in a circuit that's running at 1 kilohertz. Then the transistor would appear to be operating as shown on the figure at the left. If that same transistor is now operating at 1 megahertz, now the circuit becomes more complex, including inductance and capacitance. That means we have to do more calculations. In this class, we will use the second approximation in all our work. We always need to know if our voltage source is delivering a true voltage to the load. In this case, because the load is 1 kilo ohms and the internal resistance is 1 ohm, we say that we have a stiff voltage source. What would happen if the load is only 10 ohms and the internal resistance is 1 ohm? Then we could do some calculations using the voltage divider equation, and we would see that the actual load voltage is only 9 volts, which is a bad situation. For stiff voltage, the load resistor must be greater than or equal to 100 times the internal resistance. In this case, the load resistor must be 100 ohms or greater. What happens if we have a current source of 10 milliamps, but with an internal resistance of 10 kilo ohms and a load of 10 kilo ohms? Without doing any calculations, we would see that the current delivered to the load is only 5 milliamps. Again, this is a problem. For a stiff current source, the internal resistance must be greater than or equal to 100 times the load resistance. In this case, solving for low resistance, we see that the load resistance be less than or equal to 10 kilo ohms. We can check to see if our circuit is working better by using the current divider equation. In this case, we do the calculations, we see that we have 9.9 milliamps being delivered to the load. The purpose of using Thevenin is to take a complex circuit like the one on the left and convert it to a simplified circuit like the one on the right that only contains the Thevenin voltage and the Thevenin resistance. Then we can add a load and do repetitive calculations. In order to calculate the Thevenin voltage, we eliminate the load and replace it with a voltmeter. Then the Thevenin voltage is the voltage dropped across the 3 kilo ohm resistor. We can calculate the Thevenin voltage with the equation shown, and we see that the Thevenin voltage is 24 volts. Next, we calculate Thevenin resistance. First, we eliminate the power supply and replace it with a wire. Then we insert an ohm meter in place of the voltmeter. We can go in stages by first calculating 6 kilo ohms in parallel with 3 kilo ohms, and we find that it is 2 kilo ohms. Finally, we calculate Thevenin resistance by adding 2 kilo ohms plus 4 kilo ohms, and so Thevenin resistance is now 6 kilo ohms. Here is a circuit that has been Thevenized, and so it's much more simple and can be used for repetitive calculations as when you are changing different loads. From Thevenin voltage, you can go to Norton current by using Ohm's law, where you take Thevenin voltage divided by Thevenin resistance, and you come up with Norton current. In this case, is 4 milliamps.